Let me tell you about a number that defines humanity's place in the cosmos, a number that captures both our ambition and our limitation, our dreams and our constraints. It's a number that sounds like a death sentence for interstellar travel, but which properly understood reveals something far more interesting and hopeful: 75,000 years one way. That's how long it would take to reach the nearest star system using our current fastest spacecraft technology. 75,000 years. The entire span of human civilization, from cave paintings to smartphones, is about 10,000 years. The journey to our nearest stellar neighbor would take 7.5 times longer than all of recorded human history. This number seems to close the door on interstellar travel. It seems to imprison humanity in our solar system forever. It seems to say that the stars will always remain points of light in the sky, never destinations we can actually reach. But this number is also misleading. It's based on current technology we know how to improve. It's based on conventional propulsion we know how to transcend. And it ignores the physics of time dilation physics that fundamentally changes what 75,000 years means for a traveler. Let me take you through the calculation, because understanding how scientists arrived at this number and what it really means reveals the true landscape of interstellar travel. Let me start with the destination, the nearest star system to our Sunday. The nearest star to Earth, other than the Sun, is Proxima Centauri. It's part of a triple star system called Alpha Centauri, which includes two Sun-like stars, Alpha Centauri A and B, orbiting each other, with the small red dwarf Proxima Centauri orbiting them both at a great distance. Proxima Centauri is about 4.24 light years from Earth. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers. So Proxima Centauri is about 40 trillion kilometers away. To put this in perspective, the Moon is about 384,000 kilometers away. Mars, at its closest approach, is about 55 million kilometers away. Pluto, at its average distance, is about 5.9 billion kilometers away. Proxima Centauri is about 270,000 times farther than the distance from Earth to the Sunday. It's about 7,000 times farther than Pluto. The distances involved in interstellar travel are not just large, they're of a completely different magnitude than anything we've experienced in space exploration. And yet, in cosmic terms, Proxima Centauri is incredibly close. It's our nearest neighbor. The Milky Way galaxy is about 100,000 light years across. Proxima Centauri is a tiny step less than 1/20,000th of the galaxy's diameter. If the galaxy were the size of the United States, the distance to Proxima Centauri would be about the length of a football field. But that football field, at our current speeds, would take 75,000 years to cross. Now let me explain how scientists calculated this travel time. The calculation is straightforward. Divide the distance by the speed. The distance to Proxima Centauri is about 40 trillion kilometers. The speed depends on what spacecraft we're considering. The fastest spacecraft humanity has ever built is the Parker Solar Probe, which reached speeds of about 700,000 kilometers per hour, about 0.064% of the speed of light. At this speed, the journey to Proxima Centauri would take about 6,500 years. But the Parker Solar Probe achieved that speed by diving close to the Sun and using the Sun's gravity to accelerate. It's not heading toward any star, and it couldn't sustain that speed on an interstellar trajectory. The fastest spacecraft actually leaving the solar system is Voyager 1, launched in 1977. Voyager 1 is traveling at about 61,000 kilometers per hour, about 17 kilometers per second. At this speed, The journey to Proxima Centauri would take about 75,000 years. This is the number, 75,000 years one way. To be precise, Voyager 1 is not heading toward Proxima Centauri, it's heading in a different direction entirely. If it were aimed at Proxima Centauri and maintained its current speed, it would arrive in about 75,000 years. Let me put this number in human terms. Homo sapiens has existed for about 300,000 years. Modern human civilization, agriculture, cities, writing has existed for about 10,000 years. Recorded history spans about 5,000 years. A 75,000-year journey is longer than any human institution has survived. It's longer than any language has remained intelligible. It's longer than any building has stood, any nation has endured, any culture has persisted in recognizable form. If we had launched a spacecraft toward Proxima Centauri when Homo sapiens first emerged in Africa, it would still have about 225,000 years to go. This time frame is utterly incompatible with human planning, human patience, human life. No individual could live to see the end of such a journey. No organization could maintain coherence over such a span. No society could sustain a project through such an interval. 75,000 years is not a travel time, it's a geological epoch. It's not a mission duration, it's an extinction event. At the scale of human experience, it might as well be forever. And yet, scientists take this number seriously. They study it, refine it, look for ways around it, because despite its seeming impossibility, this number is not fixed. It's a function of our current technology. And technology changes. Now, let me explain what determines this travel time and how it could be reduced. The fundamental equation is simple. Time equals distance divided by speed. The distance to Proxima Centauri is fixed. We can't make the star any closer. So the only way to reduce travel time is to increase speed. How fast would we need to go for the journey to take a more manageable time? At 1% of the speed of light, about 3,000 kilometers per second, the journey would take about 425 years. Still multi-generational, but within the conceivable scope of a civilization. At 10% of the speed of light, about 30,000 kilometers per second, the journey would take about 42 years, a single human lifetime. Someone born the year the spacecraft launched could live to see it arrive. At 50% of the speed of light, the journey would take about 8.5 years, a reasonable mission duration like a long deployment or a PhD program. At 90% of the speed of light, the journey would take about 4.7 years in Earth time and significantly less in ship time due to relativistic time dilation. We're now in the realm of what a human crew could experience as a few years. So the question becomes, can we achieve these speeds? What would it take to accelerate a spacecraft to 1%, 10%, or 50% of the speed of light? Let me explain the physics of spacecraft propulsion. All rockets work by the same basic principle. Throw stuff out the back, and the reaction pushes the spacecraft forward. This is Newton's third law. Every action has an equal and opposite reaction. The effectiveness of a rocket depends on two things: how fast it throws stuff out the back, the exhaust velocity, and how much stuff it has to throw, the propellant mass. The relationship is captured by the Tsiolkovsky rocket equation, one of the most important equations in space exploration. It tells us that to achieve a certain velocity change, the spacecraft needs a certain ratio of initial mass, including propellant, to final mass after propellant is used. The equation reveals a harsh reality. For any given exhaust velocity, achieving higher speeds requires exponentially more propellant. If you want to go twice as fast, you don't need twice as much fuel, you need far more, because you're also accelerating the fuel itself. For conventional chemical rockets like those that took us to the moon, the exhaust velocity is about 4.5 kilometers per second. To reach even 1% of light speed using chemical rockets, the mass ratio would be absurdly large, far beyond anything we could ever build. You would need more fuel than exists in the observable universe. Chemical rockets are simply not capable of interstellar travel. The physics doesn't work. No amount of engineering can overcome the fundamental limitation of low exhaust velocity. This is why Voyager 1, using chemical rockets and gravitational assists, travels at only 17 kilometers per second, about 0.006% of light speed. At this speed, interstellar travel takes tens of thousands of years. To do better, we need propulsion systems with higher exhaust velocities, systems that can throw stuff out the back much faster than chemical reactions allow. Let me describe the propulsion technologies that could reduce the 75,000-year travel time. The first improvement is nuclear propulsion. Nuclear thermal rockets heat a propellant, usually hydrogen, using a nuclear reactor. The hot gas expands and is expelled out the back. The exhaust velocity is about twice that of chemical rockets, around 9 kilometers per second. This is better, but not transformative. A nuclear thermal rocket could reach Proxima Centauri in perhaps 40,000 years instead of 75,000. An improvement, but still far beyond human timescales. Nuclear pulse propulsion is more radical. Instead of heating propellant continuously, the spacecraft would explode small nuclear bombs behind it, riding the shock waves. This is the principle behind Project Orion, studied by the US government in the 1950s and 1960s. Project Orion could, in principle, achieve exhaust velocities of 30 to 40 kilometers per second, about 10 times better than chemical rockets. A spacecraft using this technology might reach Proxima Centauri in 10,000 years or so. Still too long for human planning, but we're making progress. Nuclear fusion propulsion would be even better. If we could achieve controlled fusion, the energy source that powers the sun, we could heat propellant to even higher temperatures, achieving exhaust velocities of 100 kilometers per second or more. A fusion rocket might reach Proxima Centauri in a few thousand years. We're getting into timescales that, while still beyond individual human lives, start to seem conceivable for long-term civilizational projects. But even fusion has limits. To reach a significant fraction of light speed, 10% or more, we need something more radical. The second major improvement is ion propulsion and related technologies. Ion engines accelerate propellant using electric fields rather than chemical reactions or nuclear heat. The exhaust velocities can be much higher, 30 to 50 kilometers per second for current designs, potentially 100 to 500 kilometers per second for advanced versions. Ion engines have low thrust. They push gently, not powerfully, but they can run for long periods, gradually building up speed. Several spacecraft have used ion propulsion, including NASA's Dawn mission to the asteroid belt. With advanced ion propulsion, travel times to Proxima Centauri might be reduced to a few hundred years, 100 times better than Voyager, but still multi-generational. The third major improvement is antimatter propulsion. Antimatter is the ultimate fuel. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy. Compare this to nuclear fusion, which converts about 0.7% of mass to energy, or nuclear fission at 0.1%, or chemical reactions at 0.00001%. An antimatter rocket could, in principle, achieve exhaust velocities approaching the speed of light. The theoretical efficiency is extraordinary. A spacecraft with a reasonable mass ratio could reach 10%, 20%, even 50% of light speed. At these speeds, Proxima Centauri is reachable in decades rather than millennia. The 75,000-year journey becomes a 50-year journey, or a 20-year journey, or less. The problem, of course, is that we can barely make antimatter at all. The total amount of antimatter ever produced by humanity is measured in nanograms. Making enough for a spacecraft would require vast production facilities and unimaginable amounts of energy. This isn't impossible, it's just extremely difficult. An advanced civilization with access to enormous energy resources could, in principle, produce the antimatter needed for interstellar travel. The fourth approach is beam power propulsion, the approach that might be most achievable with near-term technology. Instead of carrying fuel, the spacecraft is pushed by a beam of energy from home, typically a powerful laser. The spacecraft carries a large sail that reflects the laser light, gaining momentum from the photons. This is the principle behind the breakthrough Starshot project, which aims to send tiny spacecraft to Alpha Centauri at 20% of light speed. At this speed, the journey would take about 20 years. The key advantage of beamed power is that the spacecraft doesn't need to carry its fuel. The mass ratio problem that limits rockets doesn't apply in the same way. The energy source stays at home, beaming power to the spacecraft as it accelerates. The breakthrough Starshot design envisions spacecraft weighing just a few grams, essentially chips with cameras and communications equipment attached to lightweight sails a few meters across. A ground-based laser array would accelerate these tiny craft to 20% of light speed in just minutes. At this speed, they would reach Proxima Centauri in about 20 years. They would fly through the system at tremendous speed. There's no way to slow down without carrying fuel, but they could take pictures and measurements and transmit them back to Earth. The data would arrive about 4 years later for a total mission time of about 24 years from launch to data reception. This is a feasible interstellar mission with technology that's challenging but not impossible. The laser array would need to be enormous, perhaps a square kilometer of laser emitters, and would require gigawatts of power. But it could be built with extensions of current technology, not science fiction. Breakthrough Starshot aims to launch its first mission in the coming decades. If successful, it would be humanity's first interstellar spacecraft, the first object we've sent to another star. But there's a crucial limitation. The Starshot spacecraft are tiny. They can carry instruments but not people. Sending humans to the stars requires much larger spacecraft, which are much harder to accelerate. In part 2, I want to explore what it would actually take to send humans to the nearest star, the engineering challenges, the timescales involved, and the surprising ways that physics itself might help us. So we've established the daunting number, 75,000 years, to reach Proxima Centauri using current technology. We've explored the propulsion options that could reduce this time: nuclear rockets, ion engines, antimatter drives, laser sails. We've seen that the breakthrough Starshot project might send tiny probes to Alpha Centauri in just 20 years. But tiny probes are not humans. Sending people to the stars is a fundamentally different challenge. The spacecraft must be large enough to support human life for years or decades. It must protect against radiation, provide food and water and air, maintain psychological health over long isolation, and it must be accelerated to high speeds despite its enormous mass. Now I want to explore what it would actually take to send humans to the nearest star. What are the realistic timescales? What engineering challenges must be overcome? And how does the physics of relativity change the calculation in surprising ways? Let me start by examining what a human-carrying starship would require. A crewed interstellar spacecraft would need to be large, not just for living space, but for all the systems required to keep humans alive for years or decades. Life support systems would need to recycle air and water with near-perfect efficiency. On a journey lasting decades, you can't carry all the consumables you need. You must recycle them. The International Space Station recycles about 90% of its water. An interstellar ship would need to do better, approaching 100%. Food production would likely be necessary. Carrying decades' worth of food is impractical. Growing food aboard the ship is more feasible, but requires space, energy, and careful management. Hydroponic farms, algae cultivation, perhaps even small-scale agriculture would be needed. Radiation shielding is essential. Beyond the solar system, cosmic rays bombard spacecraft continuously. Shielding adds mass, lots of mass. A heavily shielded habitat module might weigh hundreds or thousands of tons. Redundancy is critical. On a journey measured in decades, equipment will fail. Every critical system needs backups, and the crew needs the ability to manufacture replacement parts. A machine shop, a 3D printing facility, stores of raw materials all add mass. Propulsion systems, fuel, power generation, communications equipment, scientific instruments, landing vehicles if the destination includes a planetary surface, the list goes on. A realistic crewed interstellar spacecraft might have a dry mass of thousands of tons, possibly tens of thousands. Now let's calculate what it would take to accelerate such a spacecraft to useful speeds. The Tsiolkovsky rocket equation tells us the relationship between exhaust velocity, mass ratio, and final velocity. For a given exhaust velocity, higher speeds require exponentially more propellant. Let's consider a spacecraft with a dry mass of 10,000 tons, roughly the mass of a large naval vessel, probably a minimum for a self-sufficient interstellar habitat. With chemical rockets, exhaust velocity to 4.5 kilometers per second, reaching even 100 kilometers per second would require a mass ratio of about 10 billion. That's 100 billion tons of propellant. Impossible. With nuclear thermal rockets, exhaust velocity to 9 kilometers per second, reaching 100 kilometers per second requires a mass ratio of about 100,000. That's a billion tons of propellant. Still impossible with any conceivable technology. With advanced ion engines, exhaust velocity to 100 kilometers per second, reaching 1,000 kilometers per second, requires a mass ratio of about 22,000. That's 220 million tons of propellant. Better, but still enormous. With nuclear pulse propulsion, exhaust velocity to 40 kilometers per second, reaching 3,000 kilometers per second, 1% of light speed requires a mass ratio of about 1,000. That's 10 million tons of propellant, challenging but perhaps not impossible for a sufficiently advanced civilization. With antimatter propulsion, exhaust velocity approaching light speed, the mass ratios become much more manageable. Reaching 10% of light speed might require a mass ratio of only 2 to 3. That's 20,000 to 30,000 tons of propellant, including the antimatter and whatever reaction mass is used. This is why antimatter is so appealing for interstellar travel. It's the only propulsion technology that makes the mass ratio problem tractable for high-speed crewed missions. But antimatter has its own challenges. We currently produce only nanograms per year at enormous cost. Scaling up to tons would require revolutionary advances in production and storage technology. Let me now consider the realistic timescales for crewed interstellar missions with different technologies. With nuclear pulse propulsion at 1% of light speed, the journey to Proxima Centauri would take about 425 years. This is a generation ship scenario. The crew that launches would not live to arrive. Multiple generations would be born, live, and die aboard the ship. Their descendants would eventually reach the destination. Generation ships raise profound ethical and practical questions. Is it right to launch people on a journey they cannot complete, condemning their children and grandchildren to life aboard a ship? Can social stability be maintained over centuries? What happens if the ship develops problems, mechanical failures, disease outbreaks, social breakdown with no possibility of rescue. These challenges are formidable, but perhaps not insurmountable. Humans have lived in isolated communities for generations, remote islands, isolated valleys. A well-designed generation ship might sustain a small society for centuries. With antimatter propulsion at 10% of light speed, the journey would take about 42 years. This is within a single human lifetime, though still a substantial fraction of it. A 30-year-old astronaut would arrive at age 72 elderly, but still alive. At 10% of light speed, time dilation is minimal, only about 0.5%. The ship time and Earth time are nearly identical. The crew would experience nearly the full 42 years of the journey. With more advanced propulsion at 50% of light speed, the journey would take about 8.5 years in Earth time. Time dilation becomes significant. Ship time would be about 7.4 years. The crew would age less than people back on Earth. At 90% of light speed, the journey would take about 4.7 years in Earth time, but only about 2 years in ship time. The relativistic effects become substantial. At 99% of light speed, the journey would take about 4.3 years in Earth time, but only about 7 months in ship time. Time dilation compresses the subjective journey dramatically. This is the remarkable gift of special relativity. The faster you go, the less time passes for you. A journey that takes decades in Earth time can be experienced as months or years by the travelers. But there's a catch. To benefit from time dilation, you need to actually achieve these speeds. And as we've seen, achieving 90% or 99% of light speed requires propulsion technology far beyond what we can currently build. Let me now discuss the energy requirements for high-speed interstellar travel. Energy is the fundamental constraint. Accelerating mass to high velocities requires enormous energy. The kinetic energy of a spacecraft increases with the square of its velocity, double the speed, quadruple the energy. At 10% of light speed, the kinetic energy of a 10,000-ton spacecraft is about 4.5 times 10, 20 joules. This is roughly equal to the world's total energy consumption for 15 years. At 50% of light speed, the kinetic energy is about 1.5 times 10, 21 joules, 5 times more, roughly the world's total energy consumption for 50 years. At 90% of light speed, relativistic effects increase the energy dramatically. The kinetic energy is about 1.3 times 10, 22 joules, the world's total energy consumption for 400 years. These numbers sound impossibly large, and they are if we're thinking about current energy production. But they become more tractable when we consider the energy resources available in the solar system. The sun outputs about 3.8 times 10, 26 watts. The energy to accelerate a spacecraft to 10% of light speed is equivalent to the sun's output for about 1.2 seconds. If we could capture even a tiny fraction of the sun's output using solar collectors or a partial Dyson swarm, we would have more than enough energy for interstellar missions. A solar collector covering 0.1% of the sun's surface would capture about 3.8 times 10, 23 watts, enough to accelerate our hypothetical spacecraft to 10% of light speed in about 20 minutes. This suggests that the energy for interstellar travel exists in abundance. The challenge is not the fundamental availability of energy, but our ability to capture and use it. A civilization that has expanded to harness significant solar energy, what is sometimes called a Kardashev Type II civilization, would have the energy resources to routinely send crewed missions to other stars. The 75,000-year travel time that constrains us today would be reduced to decades or less. Now let me explore a different approach. Rather than speeding up the journey, we could extend human lifespan. If humans live for thousands of years, the 75,000-year journey would become more conceivable, still long but not impossibly so. The journey would be tedious but not multi-generational. Life extension is speculative, but not entirely science fiction. Research into aging has identified specific biological mechanisms, telomere shortening, cellular senescence, accumulated damage that cause aging. Some organisms appear not to age at all. In principle, the mechanisms of aging might be slowed, halted, or even reversed. If human lifespan could be extended to, say, 1,000 years, a 75,000-year journey would span 75 lifetimes. Still daunting, but not fundamentally different from what our ancestors accomplished through generation ships. If lifespan could be extended indefinitely, true biological immortality, then even the 75,000-year journey becomes personally achievable. You would spend most of your life in transit, but you would arrive. Of course, the psychological and social challenges of a 75,000-year journey, even for an immortal, would be immense. The isolation, the monotony, the separation from everything and everyone you knew, these would require extraordinary psychological resilience. But life extension combined with modest speed improvements could make interstellar travel much more feasible. A spacecraft traveling at 1% of light speed would reach Proxima Centauri in 425 years. If the crew had lifespans of 500 years, the journey would be long but survivable within single lifetimes. Another approach is suspended animation, slowing biological processes so that subjective time passes more slowly. Some animals already do this naturally. Tardigrades can enter cryptobiosis, surviving extreme conditions in a dormant state for decades. Wood frogs freeze solid in winter and revive in spring. Various bacteria can form spores that remain viable for millions of years. If humans could be put into suspended animation, their metabolism slowed dramatically or stopped entirely, they could survive journeys of arbitrary length. The 75,000-year trip would feel like no time at all. You would go to sleep near Earth and wake up at Proxima Centauri. The challenges are substantial. Human biology is not designed for suspended animation. Freezing causes ice crystal formation that damages cells. Maintaining a dormant state for thousands of years without degradation seems extraordinarily difficult. But research continues. Vitrification cooling tissue so rapidly that ice crystals don't form has successfully preserved small organisms and some tissues. Medical hypothermia already slows metabolism to extend survival time during surgeries. The gap between current capability and interstellar hibernation is vast, but not necessarily unbridgeable. If suspended animation became practical, it would transform interstellar travel. Speed would become less important. Even Voyager's leisurely 75,000-year pace would be acceptable if the passengers were sleeping through it. Now let me discuss the destination itself, because Proxima Centauri is more interesting than just a point in space. Proxima Centauri is a red dwarf star, much smaller and cooler than the Sunday. It's about 12% of the Sun's mass and 15% of the Sun's diameter. Its luminosity is only about 0.17% of the Sun's. It's very dim. But Proxima Centauri has something remarkable, a planet in its habitable zone. In 2016, astronomers confirmed the existence of Proxima Centauri b, a planet with a minimum mass of about 1.3 Earth masses, orbiting at a distance of about 7.5 million kilometers, about 5% of Earth's distance from the Sunday. At this distance from the dim red dwarf, the planet receives about the same amount of energy as Earth receives from the Sunday. This puts Proxima b in the habitable zone, the region around a star where liquid water could exist on a planet's surface. We don't know if Proxima b actually has liquid water or an atmosphere or conditions suitable for life, but the possibility is tantalizing. The journey to Proxima Centauri is not just an abstract exercise. There's a potentially Earth-like planet waiting at the destination. The first interstellar mission might find a world that could one day be a second home for humanity. But Proxima b has challenges too. Proxima Centauri is an active star producing frequent flares that would bombard any nearby planet with radiation. The planet is probably tidally locked, with one face always toward the star and one always away. The conditions might be harsh. Still, the presence of a potentially habitable planet transforms the calculation. The 75,000-year journey, or the 4-2-year journey, or the 2-0-year probe mission has a destination worth reaching. Now let me address what scientists have actually calculated about realistic mission scenarios. Various research groups have studied interstellar mission concepts in detail. Let me describe some of the most developed proposals. Project Longshot was a NASA and US Naval Academy study in the late 1980s. It proposed an unmanned probe to Alpha Centauri using nuclear pulse propulsion. The spacecraft would weigh about 400 tons and travel at about 4.5% of light speed, reaching its destination in about 100 years. Project Longshot was never built. It remained a paper study, but it demonstrated that interstellar probes were at least theoretically possible with extensions of known technology. Project Daedalus was a British Interplanetary Society study in the 1970s. It proposed a massive spacecraft, 54,000 tons at launch, using nuclear fusion propulsion. The design used pellets of deuterium and helium-3, ignited by electron beams, to achieve exhaust velocities of about 10,000 kilometers per second. Daedalus would reach Barnard's star, about 6 light years away, in about 50 years, traveling at about 12% of light speed. It was designed as a flyby mission. It would pass through the target system at high speed, gathering data but not stopping. The Daedalus study was remarkably detailed, producing engineering specifications for many spacecraft systems. It showed that interstellar travel was possible within the laws of physics, even if the technology to build it didn't yet exist. Project Icarus is a contemporary follow-up to Daedalus, updating the design with modern technology and knowledge. The Icarus team is exploring various propulsion options, including fusion, antimatter, and hybrid systems. The Breakthrough Starshot project, which I mentioned earlier, represents the most realistic near-term interstellar mission concept. By using laser propulsion and accepting tiny spacecraft mass, it achieves 20% of light speed with technology that could be developed within decades. Starshot would reach Alpha Centauri in about 20 years, take pictures and measurements, and transmit them back to Earth, a journey of about 24 years from launch to data reception. This is within a human career span, within the planning horizon of institutions and governments. If Starshot succeeds, it would prove that interstellar travel is possible. The first human-made object would reach another star. We would have images of an alien solar system, close-up views of another world. This would be one of the greatest achievements in human history, and it could happen within the lifetimes of people alive today. Now, let me discuss how the travel time calculation changes when we include time dilation. The 75,000-year number I started with is the time measured by observers on Earth. But as I explained in a previous video, travelers moving at high speed experience time differently. The faster they go, the less time passes for them. This effect becomes significant at speeds above about 10% of light. Let me calculate the ship time for various journey speeds. At 10% of light speed, the Lorentz factor gamma is about 1.005. Ship time is about 99.5% of Earth time. For a 2-year journey, ship time is about 41.8 years. The difference is negligible. At 50% of light speed, gamma is about 1.15. Ship time is about 87% of Earth time for an 5-year journey. Ship time is about 7.4 years. A modest but noticeable saving. At 90% of light speed, gamma is about 2.3. Ship time is about 43% of Earth time. For a 7-year journey, ship time is about 2 years. The journey is compressed significantly. At 99% of light speed, gamma is about 7.1. Ship time is about 14% of Earth time. For a 3-year journey, ship time is about 7 months. A dramatic compression. At 99.9% of light speed, gamma is about 22. Ship time is about 4.5% of Earth time. For a 2-year journey, ship time is about 2 months. At 99.99% of light speed, gamma is about 70. Ship time is about 1.4% of Earth time. For a 2-year journey, ship time is about 3 weeks. The pattern is clear. The closer you get to light speed, the shorter the journey feels to the travelers. The universe becomes accessible on human timescales, even for journeys spanning light years. But achieving these speeds is the challenge. Each additional 9, from 99% to 99.9% to 99.99%, requires roughly 10 times more energy. The engineering becomes progressively more extreme. Still, the physics is clear. Time dilation fundamentally changes the interstellar travel equation. The 75,000-year number is not a fixed sentence. It's a baseline that can be radically reduced with sufficient speed. In Part 3, I want to explore the profound implications of these calculations. What does the 75,000-year number mean for humanity's future? How might our descendants actually reach the stars? And what does it all mean for our understanding of our place in the cosmos? So, we've established the stark number, 75,000 years, to reach Proxima Centauri with current technology, and we've explored the physics and engineering that could reduce this time dramatically. We've seen that with advanced propulsion, the journey could shrink from millennia to decades, and that time dilation could compress even those decades into months or years of subjective experience. Now I want to explore what all of this means. What are the profound implications of these calculations for humanity's future? How might we actually reach the stars? And what does the 75,000-year number tell us about our place in the cosmos? Because this number is not just a calculation. It's a statement about human limitations and human possibilities. It's a measure of the gulf between where we are and where we might go. And understanding it deeply reveals something important about the nature of existence itself. Let me start by examining what the 75,000-year number tells us about our current technological position. Humanity has been a spacefaring species for only about 65 years, since Sputnik in 1957. In that time, we've sent humans to the moon, robots to every planet in our solar system, and spacecraft to the edge of interstellar space. This is remarkable progress. No other species on Earth has left the planet. No other known species anywhere has sent machines to other worlds. In cosmic terms, we've just been born as a spacefaring civilization, and already we've taken our first steps. But those first steps are humbling when measured against interstellar distances. Voyager 1, our farthest emissary, has traveled about 24 billion kilometers since its launch in 1977. This sounds impressive, and it is, but it's only about 0.06% of the distance to Proxima Centauri. At its current speed, Voyager 1 would take 75,000 years to reach our nearest stellar neighbor. If Voyager were heading that way, which it isn't, and if it were still functioning, which it won't be, it would arrive 75 millennia from now. This number captures our technological infancy. We have learned to crawl in our cosmic neighborhood, but we cannot yet walk, let alone run. The stars remain impossibly distant with the tools we currently possess. And yet, the number also captures something hopeful. We know what limits us: speed, energy, propulsion technology. These are engineering challenges, not laws of physics. The laws of physics permit interstellar travel. The engineering just hasn't caught up yet. Every major technological revolution has seemed impossible before it happened. Heavier-than-air flight was proven impossible by respected scientists until the Wright brothers flew. Breaking the sound barrier was thought to be a death sentence until Chuck Yeager did it. Landing on the moon was science fiction until Apollo 11. The 75,000-year number might seem like a barrier, but it's really a challenge. It says, here is where you are, here is how far you need to go. It invites us to close the gap. Now let me consider the different strategies for closing that gap. The first strategy is pure speed, developing propulsion systems that can accelerate spacecraft to significant fractions of light speed. As I discussed in part 2, various technologies could achieve this. Nuclear pulse propulsion could reach 1 to 5% of light speed. Fusion drives might reach 15%. Antimatter propulsion could potentially reach 50% or higher. Beamed power systems could accelerate small probes to 20% or more. Each of these technologies has challenges. Nuclear pulse propulsion requires exploding nuclear bombs, which raises obvious concerns. Fusion drives require controlled fusion, which we haven't yet achieved on Earth. Antimatter production is currently infinitesimally small and enormously expensive. Beamed power requires laser arrays of unprecedented scale. But none of these challenges are fundamental physics barriers. They're engineering problems, hard engineering problems, but solvable in principle. A civilization that devoted serious resources to interstellar travel could likely develop one or more of these technologies within centuries. The second strategy is patience, accepting slower speeds but finding ways to survive the longer journeys. Generation ships would carry populations that reproduce during the journey. The people who launch are not the people who arrive, their descendants complete the voyage. This requires social stability over centuries, reliable life support for generations, and a culture that sustains the mission across time. Suspended animation would allow travelers to sleep through the journey. If biological processes can be slowed or halted, passengers could survive trips of arbitrary duration. They would close their eyes at departure and open them at arrival, with no subjective time passing. Life extension might allow individuals to survive journeys of centuries or millennia. If aging could be slowed or reversed, the same people who launch might arrive older but still alive. Digital existence offers another possibility. If human consciousness could be uploaded to computer systems, travelers might not need biological bodies at all. They could exist as patterns of information, immune to the physical degradation that limits biological life. Each of these strategies has its own challenges: social, biological, technological, philosophical, but each offers a path to interstellar travel even without achieving high speeds. The third strategy is to change the game entirely, to find shortcuts that circumvent the tyranny of distance. Wormholes, if they could be created and stabilized, would connect distant points in space directly. Instead of traveling 4.24 light years, you would step through a portal and emerge at your destination. The distance would become irrelevant. The Alcubierre drive, if it could be built, would move space itself rather than moving through space. The ship would ride a bubble of warp space-time, potentially traveling faster than light without violating relativity. These exotic possibilities are highly speculative. Wormholes require exotic matter with negative energy density, which may not exist. The Alcubierre drive has similar requirements and may create insurmountable problems. Most physicists are skeptical that either could be achieved. But physics has surprised us before. General relativity and quantum mechanics have revealed aspects of reality that no one anticipated. A future theory of quantum gravity might open possibilities we can't currently imagine. The prudent approach is to pursue the known technologies, advanced propulsion, life extension, suspended animation, while remaining open to revolutionary discoveries that could transform the game entirely. Now let me explore what interstellar travel would actually mean for human civilization. The 75,000-year number, even when reduced by technology, implies something profound. Interstellar travel will fundamentally change the nature of human society. Consider even the optimistic scenario. Spacecraft traveling at 10% of light speed, reaching Proxima Centauri in about 42 years. This is within a single human lifetime, but it's still radically different from any journey humans have undertaken before. A round trip would take at least 84 years plus time spent at the destination. A person who left at age 30 would return at best at age 114 or older. Everyone they knew on Earth would likely be dead. The world they returned to would be transformed by nearly a century of change. This asymmetry between the experience of travelers and the experience of those who stay behind would reshape human relationships, institutions, and culture. Families would be divided not just by space, but by time. A parent who traveled to another star would return to find their children elderly or dead, their grandchildren older than themselves. The normal continuity of generations would be shattered. Nations and institutions would face unprecedented challenges. A government that launched a starship would likely not exist when it returned. The political, economic, and cultural context would be unrecognizable. How do you maintain accountability over such timescales? How do you plan for contingencies you cannot foresee? Communication would be painfully slow. A message from Proxima Centauri takes 4.24 years to reach Earth. A conversation, question, and answer takes at least 8.5 years. Real-time communication is impossible. Travelers would be profoundly isolated from home. This isolation would likely lead to independence. Colonies established at other stars would become autonomous by necessity. They couldn't wait years for instructions from Earth. They would develop their own governance, their own culture, their own identity. Over time, these separate human populations would diverge. Different environments would favor different adaptations. Different cultures would develop different values and practices. Different technologies would emerge in different places. Humanity might split into multiple species, not through conflict, but through separation. The distances between stars would become genetic and cultural barriers, dividing the human family into branches that might eventually not recognize each other as kin. This is the deep implication of interstellar travel. It's not just a journey to another place, it's a transformation of what it means to be human. The species that spreads to the stars will not remain a single species for long. Some might see this as tragic, the fracturing of human unity, the loss of common identity. Others might see it as glorious, the flowering of human potential into countless forms, the diversification of consciousness across the cosmos. Either way, it's a consequence of the distances involved. The 75,000-year number, even reduced to 42 years, represents a gulf that will reshape humanity profoundly. Now let me consider the question of why we should attempt interstellar travel at all. The costs are enormous, the risks are severe, the timescales are daunting. Why should humanity invest in reaching the stars? The first reason is survival. Earth is fragile. We face existential risks, asteroid impacts, supervolcanic eruptions, nuclear war, climate catastrophe, engineered pandemics, artificial intelligence gone wrong. Any of these could end human civilization or even the human species. As long as all humans live on one planet, we're vulnerable to extinction. A single catastrophe could end everything we've built, everything we are, everything we might become. Spreading to other star systems would provide insurance against extinction. Even if Earth were destroyed, humanity would survive elsewhere. Our eggs would no longer be in one basket. This argument becomes more compelling the longer the timescale you consider. Over millions of years, existential catastrophes become increasingly likely. The sun will eventually make Earth uninhabitable. Spreading beyond the solar system is the only long-term guarantee of survival. The second reason is knowledge. The universe is vast and largely unknown. Other star systems contain planets, moons, asteroids, phenomena we can barely imagine. Studying them up close would vastly expand our understanding of nature. Are there other living worlds? Other intelligent species? Other civilizations? We cannot answer these questions from Earth. We must go and see. The scientific discoveries waiting among the stars might transform our understanding of physics, biology, chemistry, everything. We've learned so much from exploring our own solar system. The knowledge from other systems would be proportionally greater. The third reason is growth. Human population and economy cannot grow indefinitely on Earth. There are limits to how many people the planet can support, how much energy we can harvest, how much material we can use. Spreading to other worlds removes these limits. The resources of other planets, other stars, other systems are essentially unlimited. A civilization that expands to the stars can grow without bound, not infinitely, but to scales that dwarf anything possible on a single planet. This growth is not just about numbers, but about possibilities. More people means more minds working on problems. More resources means more capacity for ambitious projects. More worlds means more diversity, more experiments, more chances to discover something wonderful. The fourth reason is meaning. Humans have always explored. We crossed oceans, climbed mountains, descended into caves, trekked to the poles. This drive to see what's over the horizon is fundamental to our nature. Interstellar travel is the ultimate expression of this drive. It represents humanity reaching for the infinite, refusing to accept limits, aspiring to something greater than ourselves. A species that stays on one planet forever has made a choice for safety, for comfort, for the familiar. A species that reaches for the stars has made a different choice, a choice for risk, for adventure, for the unknown. Both choices are valid, but the second choice is more characteristically human. It's what we've always done, pushed boundaries, taken risks, sought new worlds. Interstellar travel is the continuation of a story that began when our ancestors first left Africa. The fifth reason is that we can. The physics permits it. The engineering is challenging, but possible. The resources exist. We have the capability, in principle, to become an interstellar species. This capability confers a kind of responsibility. If we can reach the stars and choose not to, we're making a statement about what we value. We're saying that safety matters more than possibility, that the known matters more than the unknown, that comfort matters more than destiny. Some would argue this is the wise choice. Others would argue it's a betrayal of human potential. The debate is ongoing, and there's no easy answer. But the capability is real. The 75,000-year number can be reduced. The stars can be reached. The question is whether we choose to try. Now let me explore the timeline of how this might actually unfold. Interstellar travel will not happen tomorrow, or next year, or next decade. The technology required doesn't exist yet, but we can sketch a plausible timeline based on current trends and reasonable projections. In the near term, the next few decades, we might see the first interstellar probes launched. The Breakthrough Starshot project aims to send tiny spacecraft to Alpha Centauri at 20% of light speed. If the technical challenges can be overcome, building the laser array, developing the light sails, miniaturizing the instruments, the first launch might occur in the 2040s or 2050s. These probes would reach Alpha Centauri in about 20 years, with data arriving back on Earth about 4 years later. By the 2070s or 2080s, we might have the first close-up images of another star system. This would be a transformative moment proof that interstellar travel is possible, even if only for tiny robots. It would energize the field, attract funding, inspire generations. In the medium term, the next century or two, we might develop propulsion systems capable of sending larger payloads at high speeds. Advanced nuclear propulsion, early fusion drives, or beam power systems might achieve 1 to 10% of light speed for substantial spacecraft. Unmanned missions to multiple nearby star systems might become routine. At the same time, progress in life extension, suspended animation, and closed-loop life support might make human interstellar missions conceivable. The first crewed expeditions might be planned, even if not yet launched. In the longer term, centuries from now, crewed interstellar travel might become reality. If antimatter production becomes practical, or if fusion drives mature, or if breakthrough propulsion concepts succeed, spacecraft might reach 1, 0, 50% of light speed. Journeys to nearby stars would take decades rather than millennia. The first human colonies might be established at other stars. Initially small and dependent on resupply from Earth, they might gradually become self-sufficient, founding new branches of human civilization. Over millennia, these colonies would multiply and spread. Humanity would become a truly interstellar species, present at dozens, then hundreds, then thousands of star systems. This timeline is speculative, of course. Technological progress is unpredictable. We might advance faster than expected, or we might hit obstacles that delay progress for centuries. But the general trajectory seems plausible. From probes to piloted missions to colonies, spread over centuries to millennia. The 75,000-year number represents where we are today. The numbers at the end of this timeline, decades, years, months, represent where we might be in the future. The gap is vast, but not unbridgeable. Now let me consider what reaching the stars would mean for our understanding of our place in the universe. Humanity has always sought to understand where we fit in the cosmic scheme. We've developed religions, philosophies, sciences to answer this question. The answer has changed dramatically over time. Ancient peoples saw themselves at the center of a small cosmos created by gods for their benefit. The universe was intimate, purposeful, human-scaled. The Copernican revolution displaced us from the center. The Earth orbits the sun, not vice versa. We're not the center of everything. We're inhabitants of a typical planet in a typical solar system. The discovery of galaxies extended this displacement. Our sun is one of hundreds of billions of stars in the Milky Way. Our galaxy is one of hundreds of billions in the observable universe. We're smaller and less central than ever imagined. The 75,000-year number is part of this story of displacement. It tells us that the universe is vast beyond comprehension, that our current technology is puny compared to the distances involved, that we're effectively trapped in our solar system unless we make dramatic advances. But interstellar travel, if achieved, would begin a new chapter in this story. We would no longer be trapped. We would have escaped our cosmic cradle, spread to other worlds, taken our place among the stars. We would be not just inhabitants of Earth, but citizens of the galaxy. This would be a transformation of human identity. For all of history, we've been an earthbound species. Our myths, our histories, our sense of who we are, all are tied to this one small planet. Becoming interstellar would change this fundamentally. Future generations might be born under alien suns, might know Earth only as a distant ancestral home, might think of themselves as citizens of worlds we cannot yet name. This is not diminishment, but expansion. We would not be less human for spreading to the stars. We would be more human, expressing capacities we've always had but never fully realized. The 75,000-year number challenges us to begin this transformation. It says, here is the distance you must cross. Here is the obstacle you must overcome. It invites us to become what we have the potential to be. Now let me explore the philosophical implications of these distances. The light-year distances between stars raise profound questions about the nature of time, space, and existence. Consider the time dilation effects I discussed earlier. A traveler moving at 99% of light speed would experience the journey to Proxima Centauri as about 7 months, while observers on Earth would measure it as 4.3 years. This raises questions about the nature of time. Which time is real, the ship time or the Earth time? The answer, according to relativity, is that both are equally real. There's no absolute time that everyone agrees on. Time is relative, perspective, dependent, malleable. This has implications for personal identity. If a traveler ages 7 months, while their twin on Earth ages 3 years, which version of them is really older? The question becomes even more confusing on longer journeys, where travelers might return centuries younger than their great-great-grandchildren. These aren't just thought experiments. They're real consequences of real physics. If we become an interstellar species, we'll have to grapple with them practically. Consider also the communication delays. At 4.24 light-years distance, a message takes 4.24 years to travel from Earth to Proxima Centauri. A conversation question and response takes at least 8.5 years. This is fundamentally different from any communication humans have experienced before. Even the most distant telegraph required only seconds. Even the most isolated explorer could eventually report back within their lifetime. Interstellar communication is communication across time as much as across space. The person who receives your message is not the person you sent it to. They've changed, aged, evolved in the years the message was traveling. You're communicating with the future. This has implications for governance, for relationships, for the coherence of society. How do you maintain a civilization when messages take years to cross? How do you maintain a relationship when conversations span decades? The answer might be that you don't, that interstellar distances inevitably fragment human civilization into isolated pockets, each developing independently. Or the answer might be that we develop new forms of social organization adapted to these timescales, asynchronous communication, patient governance, relationships that span generations. Either way, interstellar distances force us to reconsider assumptions we've taken for granted. Instantaneous communication is the default in our experience. It would not be the default among the stars. The implications are still being understood. Now let me consider what other civilizations might have learned about these challenges. If intelligent life is common in the universe, other civilizations have probably faced the same challenges we face. They've had their own versions of the 75,000-year number, the distance to their nearest neighbor, the limitations of their early technology. How have they responded? One possibility is that they've solved the problem. Advanced civilizations might have developed technologies that make interstellar travel routine, fast propulsion, suspended animation, extended lifespans, or exotic shortcuts we can't yet imagine. If so, the galaxy might be full of interstellar travelers passing through our neighborhood without us noticing. The famous Fermi paradox, where is everybody, would be answered. They're here, but we're too primitive to detect them. Another possibility is that interstellar travel is harder than we think, that no civilization has solved the problem, that everyone is trapped in their home system. The 75,000-year number might be typical, and no one has found a way around it. If so, the galaxy might be full of isolated civilizations, each alone in their solar system, each looking at the stars and wondering who else is out there. Another possibility is that civilizations choose not to travel. They might decide that the costs are too high, the benefits too uncertain, the risks too great. They might turn inward rather than outward, developing their home systems, but never leaving. If so, the galaxy might be quiet by choice rather than by necessity. Civilizations might exist everywhere, but they stay home. Another possibility is that interstellar travel is possible but transforms civilizations so fundamentally that we wouldn't recognize the travelers as intelligent life. They might become something else. Digital minds, distributed networks, patterns of energy without physical form. If so, the galaxy might be full of travelers, but they're not looking for planets or communicating by radio. They might pass through our solar system without us having any way to detect them. Each of these possibilities has implications for our own future. We might be about to join a galactic community, or we might be about to confirm our cosmic isolation, or we might be about to transform into something we can't currently imagine. The 75,000-year number is a starting point for these speculations. It tells us what we can do now. The question is what we'll be able to do in the future and what others might have done in the past. Now let me bring this exploration to a close by reflecting on what the 75,000-year number ultimately means. 75,000 years, one way. This is the baseline, the measure of our current limitations, the distance we cannot yet cross in a human lifetime, the challenge that defines our cosmic situation. This number is daunting. It exceeds all of human history. It makes interstellar travel seem impossible, the stars forever beyond reach. But the number is also an invitation. It says, here is the gap between where you are and where you could be. It challenges us to close that gap with faster rockets, longer lives, deeper sleep, more patience. The gap can be closed. The physics permits it. The engineering is hard but possible. The timescales are long but not infinite. We can go from 75,000 years to 425 years with nuclear pulse propulsion. We can go from 425 years to 42 years with antimatter drives. We can go from 42 years to 7 months with near light speed travel and time dilation. At each step, the impossible becomes the difficult, and the difficult becomes the achievable. This is the story of human technology, a story of boundaries pushed back, limitations overcome, possibilities expanded. The 75,000-year number will not be the final word. It's a snapshot of where we are in 2026, not a permanent sentence. Our descendants will laugh at it, as we laugh at those who thought heavier-than-air flight was impossible. But the number also reminds us of what's at stake. If we fail to develop, if we destroy ourselves, or stagnate, or turn away from the stars, the 75,000-year number will remain. The gap will not close. The stars will stay forever distant. This is the choice before us. We can accept the limitation and remain earthbound forever, or we can refuse to accept it and work to overcome it. The choice is ours to make. I believe we will choose the stars. Not because it's easy, it's not. Not because it's guaranteed, it isn't. But because reaching for the stars is what humans do. It's who we are. The first humans who left Africa faced daunting distances, deserts, mountains, oceans. They didn't have the technology to know what lay ahead. They went anyway. The first sailors who crossed oceans faced journeys of months with high risk of death. They didn't have GPS or weather forecasting or satellite communication. They went anyway. The first astronauts who went to the moon faced risks that we can barely imagine today. They sat atop rockets that could explode, traveled through space with primitive computers, landed on a world no human had touched. They went anyway. Interstellar travel is the next chapter in this story. The distances are greater, the timescales longer, the challenges more severe, but the spirit is the same. The refusal to accept limits, the determination to reach beyond ourselves, the faith that the unknown is worth exploring. 75,000 years one way, this is where we start, but it's not where we'll end. The stars are waiting And someday, perhaps not in our lifetimes, but someday we will reach them. This is the meaning of the 75,000-year number. Not a barrier, but a challenge. Not a sentence, but an invitation. Not an ending, but a beginning. The journey to the stars starts here, with this number, with this understanding, with this determination to overcome it. The journey will be long and hard and uncertain. But the destination is worth any effort. The stars are calling, and humanity will answer